Imagine, for just a second, the Large Hadron Collider at CERN.
Oh, yeah. The absolute cathedral of modern physics.
Right. I mean, it's just this staggering feat of engineering. You've got 27 kilometers of superconducting magnets just, buried under the Swiss-French border.
Mhm.
And you are taking these tiny bunches of protons, you're accelerating them to, what, like 99.9999999% the speed of light?
Basically, as close to the speed limit of the universe as physical possible, yeah.
Exactly. And then you are deliberately smashing them head-on into each other.
Yeah.
It is, it's arguably the most complex, precise scientific instrument humanity has ever put together.
It really is. And, the entire goal of all that hardware, the billions of dollars, the thousands of physicists working around the clock, it's essentially to just observe what happens at the exact point of impact.
Right.
They're looking for the fundamental building blocks of reality, things like the Higgs boson, just sort of emerging from the debris of that microscopic car crash.
Yeah, and you would assume, I think anyone would assume that given the monumental scale of the engineering, the mathematics underlying those collisions is just this masterpiece of flawless logic.
You would hope so, right?
Right. You'd think the equations that tell us what to expect are perfectly behaved. But if you actually, open the hood on the math dictating that exact split-second point of impact, it doesn't work.
It completely breaks down.
The equations don't give you a neat, predictable answer. The math literally blows up in your face. It gives you infinity.
Yeah, it is. It's kind of the great open secret of quantum field theory. When particles collide at the exact same point in space and time, the fundamental equations we use to describe reality just shatter.
It's wild to think about.
The probabilities just skyrocket to infinity.
Yeah.
And obviously you cannot build a physical, measurable universe out of infinities.
It's a complete mathematical catastrophe, which brings us to today. Welcome back to another deep dive, everyone. We are super thrilled to have you with us.
Always a pleasure to be here.
And today, we have a very specific, slightly ironic, but deeply affectionate shout out to the Bus and Sigma scholars out there listening to this.
Oh, definitely. We see you guys in the comments.
We appreciate the hustle, we really do. And frankly, you asked for a serious mental workout today. You wanted us to bridge pure mathematics and high-energy particle physics. So, we are bringing the heavy plates.
We really, really are. Today's deep dive is incredibly ambitious.
Yeah. Tell them what we're looking at.
So we are looking at this stack of brilliant, just incredibly dense source material from the Erwin Schrödinger Institute. We're exploring papers on algebraic geometry, configuration space renormalization, and topological spaces.
Light reading, basically.
Okay, just casual weekend reading. But our core mission today is to essentially solve this crisis of infinity.
We're going to explore how a purely geometric concept, a trick that pure mathematicians call blowing up a singularity on a two-dimensional curve, perfectly models the exact mechanism that physicists use to fix those exploding equations of quantum collisions.
Exactly. And by the end of this conversation, you're going to understand this core mantra.
Yeah.
If you take away literally one single concept today, let it be this blow-up turns where things collide into how they collide.
I love that phrase so much, turning where into how. But before we get completely lost in the weeds, a quick roadmap. We're going to be talking about some pretty advanced topology and quantum field theory.
But we're going to ground everything in reality.
Right. We'll use a very specific, easily visualizable toy model to make the math intuitive. We aren't going to just, read textbook equations letter by letter at you.
No one wants that.
No one. We're going to describe the shapes, the actual geometry, and the mechanisms behind the physics.
Because the really incredible thing about this topic is that the sheer elegance of the solution, you don't need to be a postdoc at CERN to appreciate it. You just need to be able to visualize a graph fundamentally changing its shape.
Okay, so let's establish the stakes here. Let's look at the physics problem first. Because to understand the cure, we really have to deeply understand the disease. Why does quantum field theory break down at the point of collision?
Well, to get a grip on this, we kind of need to look at the history and specifically transition into what is known as the position space formulation of quantum field theory.
Okay.
Specifically, our sources today focus heavily on the Epstein-Glaser approach to position space.
Now, I want to clarify something for the audience who might be slightly familiar with basic particle physics. Usually when people talk about calculating particle interactions, they talk about momentum space, right?
That's the standard way it's taught.
Like they draw those famous Feynman diagrams, the squiggly lines representing photons and the straight lines representing electrons. And they're calculating the momentum of the particles coming in and going out.
Right. And that momentum space approach is highly practical. It's what they actually use for calculating the scattering cross-sections that they physically measure at the LHC. But the problem of the infinities, these ultraviolet divergences, as they are technically called, they are sometimes a lot easier to diagnose if we look at the problem geometrically.
Meaning in position space.
Exactly. In position space.
Because in position space, we aren't primarily tracking how fast the particles are moving or their momentum vectors. We are tracking exactly where they are on the actual grid of space-time.
Precisely. In perturbative QFT, we are trying to calculate probability amplitudes. And in this Epstein-Glaser position space framework, these amplitudes are represented mathematically as distributions on a space-time manifold.
Now, the word distribution in math can be a bit, slippery for people. It's not just a scatter plot of random data points.
No, not at all.
The way I understand it from the sources specifically they draw on Laurent Schwartz's theory of distributions, it's a bit more like a density map.
That's a really highly accurate way to frame it, actually. Imagine a heat map of a massive city. The heat map doesn't just point to a single house and say it's hot here. It gives you a continuous flowing spread of temperature values across the entire geographic area.
Right, you see the red zones and the blue zones.
Yeah, exactly. In QFT, our distribution is a kind of mathematical map spread across space-time that dictates the intensity or the likelihood of fundamental interactions occurring at any given coordinate.
Okay, so let's zoom in on that. Let's imagine a microscopic, just two-dimensional patch of space-time right inside the LHC beam pipe.
Okay, I'm picturing it.
We have two particles zooming toward each other. Let's assign them actual coordinates to make this real. We'll call the position of the first particle Z1 and the position of the second particle Z2.
Now, dealing with those absolute coordinates can make the math really clunky really fast. Physicists love to simplify their variables whenever they can.
Sure.
So instead of tracking both Z1 and Z2 entirely independently, they introduce what are called relative coordinates. They define a new variable, let's call it R, which is simply the physical distance between the two particles.
So mathematically, R equals Z1 minus Z2.
Precisely. And since we are working in our simplified 2D patch of spacetime, this relative distance R has two components, right? An x-axis separation and a y-axis separation.
Right, a horizontal distance and a vertical distance.
Exactly. So we can just write R equals x comma y.
That makes perfect intuitive sense. Like if particle 1 is at an x-coordinate of 10 and particle 2 is at an x-coordinate of 6, their relative x distance is just 4. They are 4 units apart.
It works beautifully. The math is super clean until they actually interact, until they collide.
Oh, because at the exact moment of a physical collision, they are occupying the exact same point in space and time.
Right. At the moment of impact, Z1 is entirely equal to Z2, which means if you subtract them, you get 0.
So our relative coordinate r becomes exactly 0, 0.
Yes, and this specific condition, this 0, 0 coordinate in relative space, is what the literature refers to as the coincident diagonal.
The coincident diagonal. It's a very descriptive term.
It is, because if you were to graph all the possible positions of particle 1 on a vertical axis and particle 2 on a horizontal axis, the scenario where their positions are perfectly identical forms a straight diagonal line cutting right through the origin of the graph.
Oh, I see it. Okay.
That is the coincident diagonal.
And here's where the universe just seemingly refuses to cooperate with us. Because this coincident diagonal is where the equations completely and utterly fall apart.
They don't just fall apart, they explode. Our sources point out that the physical propagators, which are the mathematical functions that dictate how the influence of a particle travels through spacetime, they are highly singular.
Meaning they behave terribly at 0.
They behave absolutely terribly at 0.
Give me an example from the source material. What does one of these propagator equations actually look like on paper?
So the classic, arguably simplest example is a massless Euclidean Feynman propagator. If you look at the core of the equation, the probability amplitude is fundamentally proportional to 1 over x squared.
Yeah.
Where x, again, represents that relative separation we just talked about.
Okay, 1 over x squared. This is where the geometric intuition really starts to click for me. Let's look at the actual mechanics of that simple fraction.
Sure.
As the two particles get closer and closer together inside the collider, that distance x is physically shrinking. It's getting smaller and smaller.
And because x is sitting right there in the denominator of the fraction.
The overall value of the fraction just skyrockets. I mean, if the distance x is 0.1, then 1 over x squared is 100.
Right.
If they get even closer, say x is 0.001, the value shoots up to 1,000,000. So as the particles approach the exact same infinitesimally small point as they hit that coincident diagonal where the relative distance is truly zero, the probability amplitude shoots up to absolute, unadulterated infinity.
You are attempting to divide by zero.
Yeah.
And in calculus, when you try to integrate a function like that over a region of space that includes the 0 point, the integral simply diverges. It is, in the strict terminology of the mathematicians, non-integrable.
The math is essentially screaming that there's an infinite probability density precisely at the moment of impact.
Right.
Now, I have to stop here for a second and push back on the fundamental premise of all of this, because I'm reading these sources, right? I'm reading about the historical crisis in physics in the 1930s and 40s. You had absolute titans of physics, Paul Dirac, Werner Heisenberg, Wolfgang Pauli, and they were staring at these infinities and calling it a fundamental disease of the theory. I mean, Dirac famously hated renormalization.
Oh, he despised it. He thought it was completely mathematically unsound. He called it brushing the infinities under the rug.
Right, he did. And from a completely lay perspective, Dirac seems completely justified in being mad about it. Well, think about it. If my accountant uses a financial model that occasionally tells me I owe infinite taxes, I don't just accept it. I fire the accountant and throw out the broken model.
That's a fair point.
So if a scientific theory predicts that a physical event has an infinite probability, which is totally impossible in our finite physical reality, why didn't physicists just throw out quantum field theory? Doesn't the sheer existence of the infinity prove the theory is fundamentally wrong?
See, that is the exact philosophical crisis the entire field faced for like 2 straight decades. It's a completely valid challenge. Why keep a broken theory?
Exactly.
But the answer is rooted in a deeply pragmatic, almost desperate reality. Everywhere except that exact microscopic point of collision, quantum field theory is the most accurate, breathtakingly successful scientific theory ever conceived by the human mind.
It's the theory that gives us the magnetic moment of the electron, right?
Yes, QED, which is a subset of quantum field theory, predicts the anomalous magnetic dipole moment of the electron to an accuracy of better than 1 part in a trillion.
It's hard to even wrap your head around that level of precision.
It matches experimental data at CERN to a degree of precision that is, frankly, difficult to comprehend. We've never had a theory this good.
So it's kind of like having a map that successfully navigates you across an entire massive continent, predicting every river, every mountain pass, every valley with literal millimeter precision.
Right.
But right in the dead center of the map, covering the exact destination you ultimately want to reach, there is a giant obscuring ink blot of infinity. You don't throw away the entire map because of the ink blot. You try to figure out what's underneath it.
Exactly. You find a way to read through it. And the mathematical process of figuring out how to read the map through that ink blot, that is a process of renormalization.
Renormalization, okay.
Yes. Historically, figures like Richard Feynman, Julian Schwinger, and Sincero Tamanaga, they won the Nobel Prize for figuring out early, very operational ways to handle this.
Right, the early pioneers.
But as the source material from the Schrödinger Institute details today, the modern, rigorous mathematical formulation of renormalization is really the challenge of safely extending these singular distributions across those broken coincident diagonals.
We need a way to mathematically define the space right at the singularity without destroying the perfection of the theory everywhere else.
You nailed it.
Okay, so we have our broken physics, a massive smudge of infinity right at the coordinate 0, 0. Now, to fix this, our sources take a really fascinating pivot. They tell us that to solve the physics problem, we actually need to leave physics entirely for a moment.
We do. We need to walk across the university campus to the math department and dive headfirst into algebraic geometry.
Because the mathematicians have apparently been dealing with a structural failure that is remarkably similar, and they have developed an incredibly elegant topological tool to fix it.
It's a beautiful parallel.
So let's meet the math problem. The sources provide us with this really beautiful, concrete toy model to help us understand the topology of our colliding particles. It's an equation for a specific curve called a nodal cubic.
Right, so algebraic geometry at its core is the study of geometric shapes and spaces that are defined by the roots of polynomial equations.
Okay.
And the Nodal Cubic is just a classic textbook example of a shape with a severe behavioral problem.
Okay, I have the equation from the text right here in front of me. For all the bus and sigma scholars listening, to try to really picture this in your mind's eye as we describe it. The equation defining our curve is f of x comma y equals y squared minus x squared times x plus 1, and all of that equals 0.
Let's translate that math into a visual shape.
Yes, please.
If you plot that specific equation on a standard 2D Cartesian graph, just your basic x and y axes, you don't get a simple circle or a nice straight line. You get a shape that kind of resembles a ribbon with a loop twisted into it.
A looping ribbon.
Yes. Imagine a line coming in from the bottom left of the graph. It sweeps up, loops around perfectly through the origin point at 0, 0, continues to curve, crosses back over itself exactly at the origin again, and then shoots off toward the top left.
Wait, it crosses itself. That right there is the crux of the entire issue, isn't it? The curve physically intersects its own path right at the origin, the point 0, 0.
And that self-intersection is exactly what mathematicians call a singularity. Specifically, they call this type a node.
Okay, but why is a crossing line considered a mathematical failure? Like, if I draw a figure 8 on a piece of paper right now, the center where the lines cross isn't broken. It's just ink crossing ink on a page. Why does algebraic geometry treat this node as a crisis?
It all comes down to the fundamental concept of a tangent line.
Okay, unpack that for me.
So in calculus, you want to be able to find the tangent, which is the exact trajectory or direction the curve is pointing at any given specific point. If you pick any point on the smooth outer loop of that ribbon, there is one unique straight line that perfectly grazes that point. It has a clearly defined direction.
Right, I can picture that. But at the origin.
At the origin, where the curve literally crashes into itself, which way is it pointing?
Oh, I see.
Is it pointing along the path of the line, coming up from the bottom, or is it pointing along the path of the line, looping back down from the top?
It's basically pointing in two completely different directions at once.
Exactly.
Yeah.
It has lost its unique tangent. To see this mathematically, we have to look at the lowest degree terms of our polynomial equation.
Okay, let's do the math.
Near the origin, where your x and y coordinates are just tiny, tiny fractions, the higher powers of those numbers become incredibly small.
Right, because squaring a fraction makes it smaller.
Yes. So if you expand our original equation, y squared minus x squared times x plus 1 equals 0, you get y squared minus x cubed minus x squared equals 0.
Okay, I see that expansion.
Now, if x is, say, 0.01, then x cubed is 0.000001.
Wow. Okay, so it's microscopic.
And it's microscopically small compared to the x squared term.
Yeah.
So that to understand the local geometry right exactly at the origin, we can effectively just ignore that x cubed term entirely.
It doesn't matter at that scale.
Right. So the leading degree part that dictates the shape of the actual intersection is just f sub 2 of x comma y equals y squared minus x squared equals 0.
And y squared minus x squared is a classic difference of squares. I remember from high school algebra.
There you go.
It neatly factors out into y minus x, all multiplied by y plus x equals 0.
Yes. And for that combined product to equal 0, basic algebra tells us that either the first part is 0 or the second part is 0, which means either y equals x or y equals negative x.
Wait, and those are the equations for two completely standard, perfectly straight lines. Y equals x is a line angling up to the right. Y equals negative x is a line angling down to the right. They literally form a perfect x right on the graph.
Which perfectly proves our visual intuition. At the origin, the nodal cubic curve has what mathematicians call a multiplicity of 2.
Multiplicity of 2.
Yes. It passes through the point 0, 0 twice simultaneously along two entirely distinct tangent directions. It creates this sharp, pinched node where the math simply cannot resolve a single clean trajectory.
So bridging this back to the physics for a second, I'm looking at this mathematical node, this looping ribbon crashing into itself at 0, 0, and I'm thinking back to our two quantum particles colliding at the coincident diagonal, where their relative distance r was also exactly 0, 0.
You're seeing the shared local geometry. This is exactly the profound connection the sources are making today. The local QFT collision problem is modeled by the exact same ambient plane of the 2D coordinate system in which our cubic curve has its self-intersecting singularity.
The origin 0, 0 is the exact point of catastrophe in both disciplines. In the physics model at CERN, it's the coordinate where the particles violently smash together, the distance goes to true 0, and the probability amplitude explodes to infinity. And in the algebraic geometry model, it's the exact coordinate where the curve crashes into itself and loses its mathematical definition.
Is a broken point in both universes.
Hmm.
The mathematical failure of the self-intercepting node is structurally identical to the mathematical failure of the coincident diagonal in quantum field theory.
Which is just incredibly exciting. Because if the mathematicians have figured out a clever way to untie the knot on their graph, the quantum physicists can theoretically adapt that exact same geometric architecture to untangle the infinity in their particle collisions.
Exactly. And the mathematical fix is, without exaggeration, one of the most brilliant conceptual leaps in topology. It's a process called desingularization, and the standard, highly formalized mathematical method to achieve it. This is work for which mathematician Heisuke Aranaka actually won the Fields Medal, is known as the blow-up.
The blow-up. I mean, it sounds violent, like we are just taking dynamite to the equation, but reading the source material, it's actually an act of radical expansion, isn't it?
It is restorative, not destructive at all.
Yeah.
The core philosophy is just brilliant. The mathematicians looked at this broken origin point and realized that trying to force the math to behave at that single paradoxical dot was just a lost cause.
So what did they do?
They made a radical decision. Let's just remove the point entirely.
Hey, wait, hold on. This is where I have to play the skeptic for a minute.
Go for it.
You can't just take a pair of mathematical scissors, cut a hole in your coordinate system, and delete the origin. Doesn't that fundamentally break the continuous topology of the entire space you are working in? I mean, you now have a universe with a literal hole in the middle of it.
That is exactly the right intuition, and it's exactly why you can't just delete it and leave it empty.
Yeah.
You have to replace it, and you replace it with something geometrically much larger.
Okay.
We remove the infinitely small broken point 0, comma 0, and in its exact place, we mathematically glue in an entirely new, higher dimensional mathematical space.
We are replacing a dimensionless point with an actual explorable space.
Yes. This new inserted space is called the exceptional divisor. And in the academic literature, it is denoted by the capital letter E.
Okay, E for exceptional divisor.
Right. And in the specific case of our 2D plane, this exceptional divisor is isomorphic too, meaning it's structurally identical to the real projective line, which is written as P superscript 1.
Okay, exceptional divisor, projective line. Let's peel back the academic jargon for a second. What is this new space actually made of?
Sure.
If I am like a tiny mathematical explorer walking along the curve toward the origin, and suddenly the origin is gone and I step onto this new exceptional divisor, what am I standing on? What do the points in this new space actually represent?
Every single point on this new exceptional divisor E represents a limiting ratio of our original x and y coordinates.
A limiting ratio.
Specifically, it represents the ratio x:y. In much simpler terms, this new space parameterizes every single possible direction you could use to approach the origin.
Okay, let me try a thought experiment to see if I am visualizing this correctly. Let's go back to a physical analogy. Imagine two cars, car A and car B, driving on an endless, perfectly flat parking lot.
Okay, I'm with you.
We are tracking them via GPS. We know their exact coordinates. The old math, the pre-blow-up math, treats their collision as a single dot on the map. They both hit the exact same GPS coordinate at the exact same millisecond. It's a massive spike of density, a singularity. The math breaks.
Right, it's just a broken coordinate.
But with a blow-up, it's like we have a magical remote control. We hit pause exactly at the millisecond of the crash. We zoom in infinitely close to that single shared GPS coordinate. And instead of just accepting that they are at the same spot, we delete the spot entirely.
And what do we put there?
We replace that intersection with a giant 360-degree compass.
I really like where this is going.
This compass doesn't record where the cars are because we already know they're at the center of the crash. The compass records the exact angle they were traveling when they made impact. It records that car A was heading due north and car B was heading southeast.
That is a phenomenal visualization. You are entirely on the mark. We are resolving the singularity into a space of approach directions.
It makes so much sense when you picture it like that.
It does. A mathematical point has no size, it has no angle, no internal geometry whatsoever. By blowing it up, we replace that featureless dot with a projective line which you can absolutely visualize at the perimeter of that compass, where every single degree on the dial is a different, distinct direction of approach.
So we have literally enacted our mantra for the episode. We replaced the where the single coordinate point with the how the compass of approach angles.
Exactly. And this sets us up perfectly to see the actual math in action. Because, understanding the compass metaphor is vital, but to truly grasp the beauty of the source material, the Bus and Sigma scholars need to see how the geometry physically transforms the equation.
Right, we have to do the math.
We need to apply this blow-up operation to our broken nodal cubic curve.
Let's do it. Let's physically untie the loop. How do we algebraically force a tiny point to become a giant compass?
We do it by fundamentally warping our coordinate system. We introduce what mathematicians call a blow-up chart.
Okay, a blow-up chart.
Remember, our compass needs to track the direction of approach, which mathematically translates directly to the slope of the line as it comes into the origin. And slope, as we all remember from algebra, is simply the rise over the run, or y divided by x.
Right. Slope equals y over x.
So let's create a brand new variable to represent that slope, that specific angle on the compass. Let's call it v.
V for velocity. No, just v.
Just v. So v equals y divided by x. If we rearrange that simple equation by multiplying both sides by x, we get y equals x times v.
Okay. Simple enough algebraic substitution.
Now, we define our entirely new coordinate grid, our x chart for the blow-up space. We will use a new variable, u, to represent our movement along the x-axis. So x simply becomes u.
Got it. X is u.
And since we just established that y equals x times v and x is now u, that means our new y coordinate is simply u times v.
Okay, let me just lock these substitution rules in my head. Everywhere in the old equation that I see an x, I'm going to replace it with f.
Correct.
Everywhere I see a y, I'm going to replace it with u times v. And we have to remember that v isn't just an arbitrary letter. It physically represents the slope, the angle of approach on our new compass.
Perfect. Now let's take our broken, self-intersecting nodal cubic equation from earlier, y squared minus x squared times x plus 1 equals 0. And let's perform what mathematicians call the pullback.
The pullback.
Yes, let's substitute our new blow-up coordinates directly into the old equation.
All right, I'll walk through it. The first term is y squared. Since y is now u times v, that becomes uv squared, which expands cleanly to u squared times v squared.
Saw it on.
The second chunk of the equation is x squared times x plus 1. Since x is now u, that becomes u squared times u plus 1. So putting it all back together, our completely new transformed equation is u squared v squared minus u squared times u plus 1 equals 0.
Great. Now look closely at the architecture of that new equation. U squared v squared minus u squared times u plus 1 equals 0. Do you notice a common architectural element in both halves of the equation?
Yes, absolutely. Both major terms are multiplied by a u squared. I can factor that out to clean up the equation.
Go ahead, factor it out. Let's see what happens.
Okay, if I pull the u squared out to the front, I get u squared multiplied by the remainder, which is v squared minus u plus 1.
Right.
Let's drop the inner parentheses to make it cleaner, so it's u squared times v squared minus u minus 1 equals 0.
And right there, with that simple factorization, you have performed the topological miracle.
Wait, really? That's it?
That's it. We have factored the equation into two entirely distinct separate pieces. Let's analyze exactly what we just did mathematically.
Okay, so the first factor is u squared equals 0.
Now, what does u actually represent in our new chart? U is essentially our original x distance. So u equals 0 corresponds to the exact center, the origin point that we blew up.
I see.
That factor, u squared, mathematically records the fact that our original curve vanished or collapsed into a singularity to an order of 2 at the origin. That u squared term represents the entire exceptional divisor itself. It is the mathematical embodiment of our compass.
Wow. Okay, and what about the second factor, the parenthesis part? V squared minus u minus 1 equals 0.
That right there is the ultimate prize. That is what algebraic geometers call the strict transform.
The strict transform.
Yes, it is the purified, clean equation of our geometric curve after the singularity has been successfully extracted and separated out. The literature typically denotes this new, healed curve as C, with a tilde over it, so C tilde. So the strict transform is C tilde. V squared minus u minus 1 equals 0.
Okay, so let me get this straight. We've cleanly algebraically split the broken curve into two independent pieces. We have the compass space, which is the u squared, and we have the strict transform curve, which is the v squared minus u minus 1.
Mm-hmm.
But how does this actually fix the visual problem of the self-intersection? I still don't quite see how it unties the knot on the graph.
To see the knot physically untie, we have to look at how our new strict transform behaves exactly on the compass itself. Remember, on the perimeter of the compass, We are sitting exactly where the old origin used to be, which means our distance variable u is exactly 0.
Okay, I follow that. So let's look at the strip transform equation right on that boundary. I take c tilde b, v squared minus u minus 1 equals 0, and I just plug in u equals 0.
Do it.
The u completely vanishes, leaving me with v squared minus 0 minus 1 equals 0, which simplifies down to just v squared minus 1 equals 0. Or, moving the 1 over, v squared equals 1.
And if a variable squared equals 1, what are the possible mathematical values for that variable?
Well, the square root of 1 is 1, but negative 1 squared is also 1, so v can equal 1, or v can equal negative 1.
Which means...
Oh, wow. Okay, let's step back and visualize what literally just happened in the geometry.
Tell me what you see.
Our original broken node at 0, 0, that single paradoxical point where the ribbon violently crashed into itself, has been completely eradicated.
Yeah.
In our new blown-up coordinate system, right on the exceptional divisor boundary where u equals 0, we don't have one messy intersecting point. We have two perfectly distinct, mathematically smooth points.
Yes. The points are u comma v equals 0 comma 1, and u comma v equals 0 comma negative 1.
And v isn't just a random coordinate. We specifically defined v as the slope, the angle of approach. If we think back to our original broken node, the two crossing branches had tangents with slopes of exactly 1 and negative 1.
Exactly. These two new points on our blown-up space are not two new singularities. They are the two geometrically resolved separation directions of the original crossing branches.
It's just so elegant.
We pulled the two intersecting lines apart by separating them into a higher dimension based entirely on their angle of approach. The curve is completely smooth now. It just doesn't intersect itself anymore.
We took a knot, and by adding a dimension of direction, the two strings of the knot just passed right by each other without ever touching. We literally turned where things collide the point 0, 0 into how they collide the specific angles v equals 1 and v equals negative 1.
It is algebraic geometry at its most absolute sublime.
It truly, truly is. But as beautiful as that pure math is, we are fundamentally a physics show today, which brings us to the most vital transition of the deep dive. Translating this math back to the reality of the Large Hadron Collider.
Right.
How does untying a loop on a pure mathematician's graph fix an exploding probability integral in quantum field theory?
This is where we bring the Rosetta Stone to life. The source material argues that we can apply this exact same geometric operation, the blow-up chart substitution, to our exploding physics equations, and it will actually resolve the infinities.
Okay, let's put it to the test. Let's test the theory.
We need an illustrative QFT kernel. Basically a simplified mathematical model of an ultraviolet or UV singularity that represents the probability distribution of colliding particles. The sources provide a really standard one for us to use. Consider the singular kernel K of x comma y equals 1 over x squared plus y squared.
Okay, the kernel K equals 1 over the sum of x squared and y squared. And just to immediately ground this in the physics we discussed earlier, x and y are the relative distance coordinates between our two particles.
Correct.
So as the particles collide, x and y both shrink to 0, the denominator goes to 0, and the entire probability fraction just explodes to infinity.
Exactly. In two-dimensional spacetime, if you try to integrate this function near the origin to find the total physical probability of the interaction, the integral diverges logarithmically. It just sums up to infinity. It is the textbook definition of our broken physics.
So we apply the mathematician's fix. We use the exact same blow-up chart we just learned.
We do. We substitute x equals u and y equals uv. But let's perform the pullback on the QFT kernel. What happens to the denominator? X squared plus y squared.
All right, substituting our new coordinates in, the denominator becomes u squared plus u squared, which expands to u squared plus u squared v squared. And just like the cubic equation, I can easily factor out the u squared. So the denominator becomes u squared multiplied by 1 plus v squared.
Spot on. So our newly transformed, pulled back kernel, which the mathematical texts denote as pi star k, is now 1 over u squared times 1 plus v squared.
Okay, I am looking at this new pulled back kernel, and I have a major concern here.
What's the concern?
We have 1 over u squared times 1 plus v squared. The u squared is still sitting right there in the denominator. U is the distance between the particles. If the particles physically collide, u goes to 0. The denominator still goes to 0. It still blows up. The blow up didn't fix the physics at all.
I know, it looks that way at first glance. But you are forgetting a fundamental, completely non-negotiable rule of calculus.
What rule?
When you change coordinate systems inside an integral, like moving from a standard Cartesian XY grid to polar coordinates, or in our specific case, moving to blow-up coordinates u, You cannot just swap the variables one for one. You have to include the area scaling factor.
Oh. Ah, the Jacobian determinant.
Yes, the Jacobian.
Right. Okay. For those who haven't taken multivariable calculus in a while, myself included, sometimes the Jacobian accounts for how the actual physical area of your coordinate grid stretches, shrinks, or warps when you change systems. If you don't include it, your calculations of area or probability will be just wildly, wildly wrong.
Exactly. And the Jacobian for our specific blow-up substitution, where x equals u and y equals uv, is simply the variable u.
Okay.
So when we rewrite the integral, our infinitesimal area element dx80 transforms into u du dv.
Okay, so to get the final mathematically accurate integral kernel, I need to multiply our pulled back kernel by the Jacobian scaling factor. So it's 1 over u squared times 1 plus v squared, multiplied by u du dv.
Let's do the algebra. When you multiply those together, what happens?
Okay, we have a u in the numerator from the Jacobian, and a u squared in the denominator from the kernel. The u on top cancels out exactly one of the u's on the bottom. So we are left with a final integral kernel of du dv over u times 1 plus v squared.
And there it is. Look very closely at that final result. Du dv over u times 1 plus v squared. This highlights the vital, profound difference between the pure geometry toy model we did earlier and the real-world physics model we are doing right now.
What happened to the u factor here compared to the cubic equation?
Wait, I see it. In the cubic equation, when we factored out the u squared, we removed it.
Wrong.
We literally dropped it from the equation to focus purely on the strict transform, the v squared minus u minus 1 equals 0. We completely erased the mathematical representation of the singularity.
But here,
In the QFT kernel, we still have a u lingering in the denominator. We have du over u.
exactly, the UV divergence hasn't magically disappeared. We didn't just erase the infinity, because you can't just delete infinity from reality.
Then what did the blow-up actually achieve? It feels like we just moved it around. We didn't just move it, we isolated it. Look at the structure of the original space versus the blown-up space. In the original uncompactified kernel 1 over x squared plus y squared, the singularity was a messy, non-integrable point, deeply entangled right in the center of our coordinate grid. It was an infinitely dense dot just ruining the entire neighborhood of space-time.
Right, the black hole in the middle of the map.
But after the blow-up, look at our result. The singularity has been transformed into a simple, highly explicit logarithmic pole, the du over u term. And most importantly, because of the geometry of our new compass space, that logarithmic pole is now isolated strictly and entirely along the boundary of the exceptional divisor, where u equals 0.
Oh, I'm conceptualizing this now. In the original math, the singularity was like a black hole sitting dead in the center of a room. In the blown-up math, the singularity has been neatly smeared and perfectly organized across the entire perimeter walls of the room, the compass boundary itself.
Precisely. We haven't solved the infinity yet, but we have perfectly contained it. We've taken an unmanageable dot and stretched it into a structured boundary that we completely understand mathematically.
This feels like the perfect moment to kind of synthesize everything we've covered so far. Let's build the Rosetta Stone of renormalization. Let's explicitly map the vocabulary of the algebraic geometry directly to the physical reality of the quantum fields, side by side, so we can really see how perfectly they mirror each other.
Let's do it. It's deeply satisfying to see these concepts align.
Okay, let's start with the root of the problem. In my mathematical toy model, I have a broken singular point at the exact coordinate 0, 0.
And in the physical world of QFT, that corresponds directly to the coincident diagonal, where the particle positions z1 equals z2. It's the physical, literal point of collision.
To fix my math, I use a blow-up procedure to create an entirely new space, the exceptional divisor, denoted as E.
In the physical theory, that exceptional divisor represents the collision boundary. It is the geometric space we physically glue into the mathematical framework precisely at the moment of impact to expand the event.
On that new space, I navigate using a slope coordinate, v equals y over x.
And that slope maps perfectly to the relative approach direction of the colliding particles. It's the angle of the crash.
When I performed the blow-up on my polynomial curve, it produced a factored term of u squared.
In physics, that term denotes the vanishing order or the multiplicity of the collision event.
But when we did the QFT integral, instead of removing the u entirely, we ended up with the factor u to the -1 times du, which is du over u.
And that explicit mathematical pole is the physical logarithmic UV divergence. It is the infinity itself, no longer a messy central point, but neatly isolated right on the boundary.
In the math, I isolated the smooth, well-behaved, strict transform curve.
That maps to the geometrically resolved physical object. It's a part of the probability amplitude that actually makes sense and accurately describes reality.
And finally, the ultimate goal, removing or managing those U factors to actually solve the equation.
That is counter-term subtraction and the mathematical extension of the distribution across the exceptional divisor E.
And that final point, counterterm subtraction, is the crucial missing link in our story today. We have successfully trapped our infinity in a neat box along the exceptional divisor boundary. But how does a physicist at CERN actually calculate the finite observable number that they eventually read off their computer screens? How do you mathematically subtract infinity from your theory without destroying the entire theory?
To understand the actual calculation, we need to perform what's called a controlled extension of the mathematical distribution. We introduce what mathematicians call a test function. Let's just denote it as phi of u comma v.
Okay.
This function is a smooth, perfectly well-behaved curve that essentially represents the physical state of the quantum system. It's the actual stuff of reality we want to measure.
Okay, so if we zoom in locally, near the collision boundary, where Albedo is approaching zero, our divergent exploding integral looks like this. The integral of phi of u comma v divided by u times 1 plus v squared, all integrated over do dv.
Correct. And the persistent threat is still that u sitting in the denominator.
Mm-hmm.
If u goes to zero, the whole integral blows up. We cannot calculate it. So physicists and mathematicians employ a brilliant, seemingly incredibly simple algebraic separation trick, a local subtraction.
Walk me through the trick, because subtracting infinity sounds like a total paradox.
We focus our attention entirely on the troublesome fraction, phi of u comma v divided by u. We're going to rewrite this fraction using a trick you literally learned in middle school algebra, adding and subtracting the exact same value to the numerator.
Okay.
Specifically, we're going to add and subtract the value of our physical test function evaluated exactly on the collision boundary, which is phi of 0 comma v.
Right. If you add 5 to an equation and then immediately subtract 5 from the same equation, you haven't changed the total true value of the equation.
Exactly. So we algebraically split our dangerous fraction, phi of u comma v over u, into two separate fractions. The first fraction becomes phi of u comma v minus phi of 0 comma v all over u.
Okay, that's first half.
The second fraction becomes phi of 0 comma v over u.
Yeah.
If you were to add those two fractions back together, the phi of 0 comma v terms in the numerators would perfectly cancel each other out, and you'd be right back where you started. We haven't changed the fundamental math at all.
Okay, I follow the algebraic manipulation, but from a bird's eye view, this just looks like we made the equation longer and significantly uglier. Why on earth do we do this?
We do it because of the miraculous, frankly beautiful behavior of that first fraction as we get closer to the collision boundary, as u approaches 0. Let's look very closely at the numerator of that first fraction. Phi of u comma v minus phi of 0 comma v.
Yeah, okay, I'm looking at it.
As u gets infinitesimally close to 0, the value of phi of u comma v gets infinitesimally close to the value of phi of 0 comma v.
Right, so you are subtracting a number from almost the exact same number. The numerator is shrinking towards 0.
Yes, and if you recall your calculus, a function minus its value at 0, all divided by the distance to 0, that looks remarkably like the formal definition of a derivative.
Oh.
If we were to Taylor expand our test function phi of u comma v around the point u equals 0, the very first term of that expansion is simply phi of 0 comma v.
Okay, let me visualize the Taylor expansion. So phi of u comma v is essentially equal to phi of 0 comma v plus u times the derivative of the function plus a bunch of higher order terms that we can completely ignore because u is tiny.
Exactly. So substitute that Taylor expansion back into our numerator. We have phi of 0 comma v plus u times the derivative minus phi of 0 comma v. What happens?
The phi of 0 comma v at the front and the negative phi of 0 comma v at the end perfectly annihilate each other. The numerator is now just multiplied by the derivative.
Precisely. And what happens to the overall fraction when you divide a numerator of u times the derivative by the u sitting in the denominator?
The u on top and the u on the bottom cancel out.
Yes. The first fraction, phi of u comma v minus phi of 0 comma v over u, is now totally regular. It is a smooth, continuous mathematical object. The u has been entirely eradicated from the denominator. There is no infinity. It is a perfectly finite, calculable number representing the smooth physical reality.
That is genuinely astonishing. And I have to be the skeptic again, I have to pull us back to reality. What about the second fraction we created? The phi of 0 comma v over u. It still has the u on the bottom. We didn't solve the infinity, we just shoved it entirely into the second fraction.
You are absolutely right to call that out. We isolated the divergence completely into that second term. But look closely at the numerator of that second fraction, phi of 0 comma v. Notice what variable is completely missing from that expression.
It doesn't have a u in it anymore. It only depends on v, the angle.
Exactly. This entire infinite term is supported strictly and exclusively on the collision locus itself, the exceptional divisor. It is purely boundary noise.
Okay. And what does a theoretical physicist do with boundary noise?
This second term yields what physicists mathematically define as a counter term. Because this infinity is now completely and cleanly isolated strictly on the boundary of our geometry, we can fundamentally define our renormalization scheme to simply subtract this specific term away. We discard it.
Wait. I need to make sure I'm grasping the magnitude of this. We algebraically split the infinity into a neat little box on the boundary of our compass. We realized it contains absolutely no smooth physical data, and we just mathematically throw it in the trash.
Geometrically speaking, yes. Renormalization, at its deepest topological level, is precisely this controlled extension of the distribution across the exceptional divisor. By using the blow-up to isolate the infinity onto the boundary, we can cleanly sever the smooth, measurable physical reality, that first fraction from the singular boundary noise, the second fraction. We subtract the noise, and we are left with the finite, incredibly precise prediction that matches what the detectors at CERN actually measure.
We blew up a singularity into a compass of angles, separated the signal from the infinite noise, and literally deleted the noise. That is incredible.
And it works to an astonishing degree of precision. It is the absolute bedrock of modern particle physics.
But this brings us to the final massive hurdle of the episode, scaling up, because the toy model we just meticulously walked through and the QFT kernel we just successfully solved was for exactly two particles colliding. A two-point example. Particle A hits particle B. The sources specifically note that this scenario only has one collision divisor. It models a single primitive divergence.
Right. And as you well know, the reality inside the Large Hadron Collider is definitely not a gentle game of two-particle billiards. It involves cascades of particles colliding in incredibly complex, nested, multi-layered ways. You have millions of interactions happening in fractions of a second.
So how does the blow-up concept scale to handle that terrifying level of complexity? I mean, let's just imagine three particles colliding. Let's call them Z1, Z2, and Z3. You don't just have one simple collision event anymore. You have a combinatorial explosion of collisions. Particle 1 could hit particle 2. Or particle 2 could hit particle 3, or particle 1 hits 3, or, God forbid, all three hit at the exact same coordinates simultaneously.
This terrifying scenario is what physicists term the threat of overlapping divergences. With three or more particles, different partial coincidence diagonals and total coincidence diagonals exist simultaneously in the math, and they overlap. For example, maybe particles 1 and 2 collide slightly before particle 3 joins them in a larger collision cluster.
In the raw, uncompactified mathematical space, these diagonals must intersect in incredibly messy, complex ways. The infinite smudges of probability all bleed into each other, creating just a giant, unreadable blob of infinity that you can't just neatly split into two fractions like we just did.
To solve this overlapping nightmare mathematically, we can't just rely on a single blowup. We have to iteratively blow up the spaces. We perform a sequence of compatible blowups on all the various configuration space diagonals.
So, if I'm visualizing this right, we replace the first two-particle collision with a compass, then we zoom into a specific point on the rim of that compass where a third particle enters the fray, and we replace that specific point on the first compass with a brand new nested compass.
That is a phenomenal way to visualize it. We are literally building compasses on top of compasses. This iterative, incredibly complex topological construction creates what algebraic geometers call Fulton-McPherson compactifications, or sometimes they're called Ducancini-Processi wonderful models.
I have to say, calling a terrifyingly complex nested geometry a wonderful model is just peak mathematician humor.
It really is. But the reason they earn the title wonderful is because of the astonishingly beautiful, clean conclusion they reach. When you iteratively blow up these spaces in the correct mathematically compatible sequence, all of those exceptional divisors, all those different nested compass boundaries you created, they eventually meet at what topology calls normal crossings.
Normal crossings. Let's break that down visually for the audience. What does a normal crossing actually look like?
It means the boundaries intersect cleanly, perpendicularly. Think of the corner of a square room where the two vertical walls and the horizontal floor all meet. They meet at perfect 90-degree angles. Instead of a chaotic mess of diagonals smashing into each other at weird, overlapping, unresolvable angles, the iterative blowups force all the boundaries of infinity, to meet at clean, perfect right angles.
Okay, I can visualize the clean corners, but why is a 90-degree intersection a major victory for a quantum physicist trying to calculate a probability?
Because a 90-degree intersection perfectly uncouples the overlapping divergences. In mathematics, if boundaries meet cleanly and orthogonally, the variables representing those boundaries are mathematically completely independent of each other.
Oh, I get it. It's like a standard XY graph. Moving along the x-axis horizontally doesn't change your y-axis vertical coordinate at all. They are entirely independent variables.
Exactly. And here's the grand finale, the massive geometric payoff of this entire deep dive. In traditional quantum physics, dealing with these overlapping nested infinities requires an incredibly tedious, famously error-prone set of recursive subtractions known in the field as the BPAT forest formula, named after Bogolyubov, Parasiuk, Hepp, and Zimmermann.
I've read about Zimmermann forests. They sound like an absolute administrative nightmare. You have to subtract a nested subdivergence, then subtract the main divergence, while constantly keeping track of combinatorial overlaps to make sure you don't accidentally subtract the exact same infinity twice.
It is a bookkeeping nightmare of the highest order. But with the geometric approach, with the Fulton-McPherson wonderful models, because the exceptional divisors are forced to meet at clean, independent normal crossings, a single, straightforward local subtraction along each wall of this resolved space is mathematically entirely equivalent to the massive, tedious Zimmermann forest formula.
You were telling me the geometry it just solves it.
The geometry is the combinatorics. The transversal perpendicular structure of these exceptional divisors beautifully and automatically encodes Zimmermann's entire recursive formula. Because they cross transversally, you just perform the simple pole subtraction we did earlier for each wall independently, one by one. The physical shape of the mathematically resolved space automatically does all the administrative bookkeeping for you.
That is staggeringly elegant. So instead of a physicist doing an infinitely recursive, headache-inducing checklist of subtractions to untangle a massive blob of colliding infinities, you just geometrically stretch the collision out into a pristine room with perfect 90-degree corners, and you calmly sweep the infinite dust off each wall, one by one.
That is perhaps the most poetic and accurate metaphor for configuration space renormalization I have ever heard in my life.
Okay, Bus and Sigma scholars, let's bring this incredible journey home. Let's summarize the ground we just covered today.
We started in the realm of pure math with a broken, self-intersecting nodal cubic curve, where the geometry collapsed and couldn't decide which way its tangent was pointing.
We stretched that microscopic point of mathematical failure into an expansive space of approach directions. We blew it up into an exceptional divisor, a projective compass, that tracked exactly how the branches crossed and replaced the broken singularity with two smooth, perfectly distinct trajectories.
Then, we took that exact same topological operation and applied it directly to the crashing infinite probabilities of quantum field theory at the Large Hadron Collider.
We definitively proved our mantra for the day. A blow-up turns where things collide into how they collide. We turned the catastrophic coincident diagonal into a clean boundary of relative approach directions. We isolated the UV divergence as a pole on that boundary so we could mathematically subtract it out, leaving us with the finite, real-world physical predictions that allow colliders to actually function and discover things like the Higgs boson.
It is a stunning, undeniable example of how the purest, most abstract algebraic geometry can perfectly resolve the messiest, most pragmatic problems in experimental physics.
But before we let everyone go, I want to pose a final thought, a conceptual question for you and the audience to just mull over as you go about your day.
I'm ready for it.
Throughout this episode, we've been treating this blow-up procedure as a math trick, right? A brilliant geometric hack to fix equations that stubbornly give us infinity. But if the only possible way to make the mathematics of quantum particle collisions yield finite, real-world physical predictions is to geometrically replace every single point of collision with a projective space of approach directions, is it really just a neat math trick?
Or is the mathematics trying to reveal something fundamentally true about reality?
Exactly. Is the math trying to tell us that at the absolute smallest, most fundamental scales of the universe, space-time itself isn't actually made of geometric points at all? Is reality fundamentally constructed out of relationships, angles, and trajectories, rather than rigid dots on a grid? If the concept of a point fundamentally crashes the universe, maybe points don't actually exist.
That is a profound philosophical question. If the Fulton-McPherson compactification is literally required for the physics of our universe to function without exploding, perhaps the fundamental structure in space-time is already blown up. Perhaps reality is, at its absolute base level, a space of directions.
Boom. Now that is something to keep you awake at night. Thank you, as always, to the Bus and Sigma scholars and everyone else for tuning in. We love taking these intense, brain-bending journeys with you. Keep questioning the math, keep looking at the underlying geometry, and keep diving deep.